Down the wrong pipe. Alright. Here we go. Focus. This is what we're listening to. Turn it down a bit. Don't need this. Actually, I want to see. Let's see if we are streaming live on the website now. Doesn't look like it. That's going to be a challenge. How to stream onto the website live. I won't get too much into that now because you guys will get bored. So instead, I will talk about some of my experimentation. So this particular experiment was hydrodynamic fusion. Hydrodynamic star jar is what it's called, but essentially this is kind of the first experiments I did for understanding waveguide. Now this top piece right here is a graphitic condom. So basically I aligned a latex glove when I was working with some graphite, some pyrolytic graphite. I got it all over my finger, right? And I just basically took my index finger and ripped it off and put it as a conductive waveguide, so it would act as a Faraday cage, and the idea was it would bounce electromagnetic waves along this wire of nitinol. I did other nitinol experiments, and they produced some interesting results, but this was by far more interesting. And the reason why it was so interesting is because the power level was very, very low. I think I didn't exceed over about 400 watts in this particular production, and I was able to boil water relatively quickly. So it was very bright, obviously. It took a long time though to breed. So it says 250 watts, but I'm gonna be safe and say 400 watts in overall. And I used potassium as my electrolyte, so it was KOH was my electrolyte, and I have the exact measurements and everything in the description below, and just in general. But yeah, I have down below a stainless steel as the anode, which is producing the oxygen, and then the nitinol is no, I guess it would be reversed. Let's see if I'm putting power into it. Yeah, so the stainless steel is the cathode, and the nitinol is the negative anode, right? I believe that's right. I might be incorrect there. All I know is electrical engineering wise, this is the negative, right? And this is the positive. And later I developed a system where you separate the oxygen, because the less oxygen you have in the system, the greater the production of not only electrical discharges you have, but also the ability to, what seems like, create a fusion response in the negative anode. I believe that's what you would consider it, is a negative anode. So it's very, very interesting response. So now this actual reaction lasted for a good hour and a half, and then I had to shut it off. The manual temperatures that I recorded were giving me some interesting data, but I really, really don't want to jump to any conclusions. Like, I have to test this over and over again, and primarily I want to test radiation and things of that nature, because the later experiments I did were far more reactive than this one. Some were a little radical, and I couldn't, like, uncontrollable, I guess you could say. But this is like probably my first experiment that netted like a positive result with nitinol, right? Yeah, so it lasted another 16 minutes, but I had other experiments later with the nitinol wire that lasted like an hour, and I just had to shut it off. I mean, what basically happens is you create a nitinol bead, like a molten core of an object, right? That is condensed, and the principle behind it is that there's a high metallic hydrogen that's being produced at its core, and you have a breeding reactor of deuterium. Now, whether that's the case or not is something that I don't have the proper measurements and sensors to detect, and that's kind of part of the principle, part and parcel of what I need to develop. So it's challenging. It's a challenging thing being an independent researcher and making sure that I check everything appropriately, because I don't want to say anything and jump to some wild conclusions that may not be true. You know, I want to make sure that what I have documented as far as the manual instrumentation has shown can be replicated and can be done through a digital source. Now, what ended up happening is here, I don't know if I can get to it now because I kind of hid those videos, but if I go to this page, yeah, I hid all the live streams, so I don't know if I'm gonna be able to do this, but we'll go into the back end and we'll find out here. And what I did is, there's one particular case where I used a carbon nanostructure, right? It was basically following Robert Murray Smith's approach, using sulfuric acid, separating, detaching carbon layers. So it was a carbon doped with sulfite, basically. I mean, that's essentially what it was. And I used that in a electrolysis process as the electrical, it would be the neutral point, the electrical medium, a substrate, and had some really phenomenal effects that I can't really explain. I mean, I can try to describe it to you guys, but it's just useless. And the video I got was really close up, so you couldn't really see the overall picture of it. But I mean, my wife's a testimonial of it. Like, she got really scared because it really went radical, and it has a lot to do with I guess it would be capillary flow, or the potential difference of air, or the gas medium and the fluid medium interacting, because that seems to be also in my research, that seems to be really important in creating any type of discharge, is that tensor breakage point, like the potential difference between gaseous medium and fluid medium, that point creates a voltage breakdown really easily, and that's something to be explored, and it's an idea that I've had, like, to be able to track that with a float, engineering wise, right? To be able to track that with a float and be able to follow it as the fluid medium goes down, like to be able to follow that tension point, and to be able to recollect the steam back into the system. Those are both aspects that need to be considered in creating this apparatus, as you would call it. So we'll see if we can get into the back end here. Now you guys know I have a Galaxy S7. All right, let's see if we can get into the back end here and find out. Basically, it was just some live streams. I think I just buried them. I don't think that they're. I didn't delete them. Let's go to. How would we get to it? We'd go into my channel. No, we go into like studio somehow, right? How do we get into the studio? Why can't I get into the studio? Let's try this again. Still don't know if this is live streaming to the website. That was the plan. It's no different than what I already had. Studio, there it is right there. Look at the negative numbers. That's because I haven't been focusing on it. Too many things, too little time. But we're gonna go to videos. Hi, my name's Dyden. Let's see if we can.
I really like skiing deep powder. I really like flying helicopters.
Intro. Wow, maybe I did delete them. I know, live. Here we go. Hopefully this will. Yeah, here we go.
With that constraint, we had to make the most of our money since the beginning.
We tried all sorts of different
Okay.
print advertising, radio advertising.
Let's see, 3D prints. 3D prints was before that. It's quite a while ago. Model T calibration. That was some hot fusion stuff that I experimented with.
Video does allow us to make an emotional connection. You know, you say a picture's worth 1,000 words, and video's worth a million.
Let's see.
Video advertising.
Electrolytic temperature testing.
We have doubled almost every year since we started.
This is what people have been waiting for all along.
I don't think this is it. partially blocked. This might be this one, because I shared it. And it has carbon involved. Yeah. This is it. Turn this off. So I have a platinum cathode, okay, and then I have a nickel anode in this particular experiment. It says right here, nickel 200 wire as a catalyst for LENR, and let's see, and the important feature is I have a spherical borosilicate chamber, okay, and then I have an outside water bath, okay, that is to measure the temperature differential. So I'm able to find out, you know, how hot it gets. Now, the problem that I have is, as you can already see, is the amount of electromagnetic pulses and radiation like bog down the sensors, right? The sensor is wrapped in Teflon, and then I also have it wrapped in aluminum, but you can see the actual webcam, which is the webcam that I'm talking to you right now with, keeps getting spiked with electromagnetic radiation, and it makes those glitches that are happening, which is unfortunate. So you can imagine what it does to the sensors. And I have Arduino sensors, so I have temperature sensors based upon Arduino. I've wrapped them in aluminum foil. It really does no good in the experiment. It keeps bogging out. Like I can log a lot of the temperature differential, but then it keeps getting spiked. It keeps getting jacked up. So then my temperature data becomes erroneous. So let's see. And this is just the breeding portion of the reactor. And so what I've added, though, let's see if I showed it. I don't think it showed it here. So here's some of the temperature data, but as you can see, it's getting bogged out. It keeps getting peaked out in the sensors, and it doesn't show. Yeah, here we go. So what I've done is I stopped the initial brooding, and yeah, you can see some of the carbon floating around. That's the heavier bits of carbon, but not to give too much away here, but as you can see, there's a tube, okay, and this is a quartz tube going straight down the center. I've added about 10 milligrams of a carbon sulfide doped solution. So it's a carbon. I'm not a chemical engineer, so I can't tell you the exact makeup of it, especially without. I have the data written down, but I don't have like the exact moles, because I use grams as my measurement. So, but it could be easily calculated. But essentially, it's carbon and a potassium electrolyte, very low amount of potassium. And I had to tune the whole thing. Like, it's a very slow process. You have to tune it. You have to ease into it, where you increase the temperature to about 40 degrees Celsius, between 40 and 43 degrees Celsius, before the reaction starts to kick in. And this is the nickel wire right here, and inside of a tube, a quartz tube. So all of the hydrogen is being produced inside of this quartz tube. On the outside is the platinum. Like, it's what's used in a lot of jewelry processes is a platinum wire mesh. So as you can see, my data is just erroneous. That's why, like I was saying, like I have some some analog sensors that I can use, and they've shown some positive, but the margin of error is like it's about 10%, and that's really way too high to really give a good accuracy prediction, right? So I don't want to go off of that. So so this is when I'm just breeding the reactor. I don't think I've added the carbon solution yet. Now the carbon solution has sulfuric. So as you can see, this I'm pulsing essentially the principle behind it, and perhaps I'm giving away too much or whatever. I don't really care. This is open source knowledge, and I'm trying to help people with their experiments. But the idea behind it is that you have to tune the cell according to the vessel. So you have to tune the circuit according to the vessel. So I'm using a borosilicate cylinder, and it relies on breeding the deuterium and having a circulatory effect, to where you're creating a flow, like a deuterium flow. And the idea is that you want to make the deuterium flow back into the negative anode. There's modifications that could probably greatly improve this, but this is what I have come about with the limited resources that I've had. So the reason why I have the Teflon on the stainless steel temperature gauge is because I don't want the stainless steel to erode from the KOH solution. Even though it's very low amount of potassium, it was just another factor. I didn't want to create any type of feedback, and I wanted to completely isolate it as much as possible. Unfortunately, I could not isolate it enough. And then you see some more plasma effects. The idea is that you, on this tip here, in this waveguide, which is what the quartz tube acts as, is not only a waveguide, but it's also concentrating the hydrogen source, is you want to make a molten ball, because a spherical object has far more capacitant value than like a straight line or a point, right? So the idea is that you build up a capacitive charge on the end of the ball, like a plasma ball, right? This is the idea behind this apparatus. That was my idea, right? That I was testing. So as I put more power into it, I did build up more of a ball, right? And the temperature raised quite substantially. You can see there's a lot of effects happening to the camera, which happens when you have more electromagnetic pulses, right? Here's where I've throttled it back. I turned it down because I really didn't want to destroy the cathode, the negative cathode. And so I throttled back. Let's see if we can get to the meat and potatoes of this, the important bits. Okay, so somewhere along the line here, after I breeded it, right, after I tried to increase the deuterium values, I knocked the camera about a bit. Let's see. Judging by the water, like there's somewhere along this point. I bet it was when I throttled back and stopped and turned it down. That's when I added the carbon solution, right? So these are nanocarbon particulate that I exfoliated. I did a ultrasonic process. Well, first off, I did it was graph oil, right, which I put in a sulfur bath, essentially. So you can use sulfuric acid, which is what I used, or you can use a sodium sulfide, like Epsom salt. But I use sulfuric acid in a distilled water solution and basically cleaved the graphite, and it created what should be a doped sulfur graphite material, right? But it's very fine particulate. And then I put it in a ultrasonification for probably about 24 hours. It was a long ultrasonification bath, and then pulled it, and then I still have it to this day, and I can use it in a solution or use it in a, you know, a ultra capacitor or whatever I want, whatever I choose to do with this particular compound. But I don't have any EDM. I don't have any way to really test its, you know, its makeup entirely. So it's unfortunate that I don't have those tools at my disposal, but you know, I still have a general idea of what it is. And basically it's a nanoparticulate graphite, a nanoparticulate carbon. So, and I can use that in my experiments. And the idea is that it would be a electron holder in a substrate. It's like a dampening effect. And somewhere along the line, I added it to the solution. I just wish that it was documented here. It still seems very clear. So let's see here. Okay, that's when I've lost a lot of water. So I'm not quite sure where I added it. This particular experiment, obviously I need to do a better job of documenting this stuff. But as you can see, the water level is decreasing, and that's gonna contribute to buoyancy. I don't know what that's about. But it's gonna contribute to buoyancy of the actual apparatus. And this is probably why, like, you know, this experiment, it's just like, people are like, what the hell? This makes no sense. But what I notice is once the water level and the tension gets close to where where the air, whatever the gaseous medium is, and the fluid medium meet, it becomes very powerful, like it usually does. I was trying to avoid it in this particular case. Now this quartz tube, this is an example, you can see it kind of banging up against the wall there, and this quartz tube actually was melted on the side. So that means that it reached a very high degree of temperature, and was banging up against the wall in this neutral state. And it's really strange. Like, actually looking at it now, this is the first time I've ever really noticed it, that you can see one part that's hot and it's basically oscillating between the wall and that. Like, that explains why the quartz tube kind of got etched. Like it had a big divot in it. I still have the tube to show, but that's very high temperature to be able to burn quartz. It's very interesting. I'd never noticed that part before. So let's go deeper into this. Yeah, I never noticed that there's two. It's kind of a binary. Yeah, I never noticed that I was like welding the quartz over there. I never noticed that in this video. Should have paid closer attention. Okay, so right about here, as it's getting super deep, like it's burned off quite a bit of the water, right? You can see the water level on the outside bath is actually starting to boil too, which is kind of interesting. And my analog sensors, you know, it was just very interesting. Like, I was surprised how fast it was slowly starting to boil. It's kind of an oxymoron, how fast it was slowly starting to boil, but no, it was really starting to take off, and there was a smell of brimstone. I'm not sure if this is actually the experiment. This might be a different one. Let's see. I'll know if the camera drops off. No. Yeah, this is it. I started it back up, so I put more distilled water in it because it was getting too low on as far as buoyancy. Like, it was starting to, the inner flask was starting to raise up to the outer water level because of the buoyancy, because of the gas to fluid ratio. But I'm not sure if this is the actual experiment. It looks like it is, because it's, yeah, see, you can see the flask is boiled off very quickly because I breeded. The idea is because it's been breeded, and there's lots of heavy water built up in that actual chamber, right? And then when I added more distilled water, it's gonna water down the deuterium, but still it's locked in place. And then I have the carbon to help it out. Okay, so yeah, you can see in a very short period of time here that water, let's see, you can see I added more carbon there in that particular case. Yeah, I turned it off, added more carbon. I think overall I added 20 milligrams of this particular carbon solution. And I cleaned it out from the outside. Some of the carbon obviously turned into steam and went into the outside chamber, which is also a major engineering problem that I need to overcome. You know, it's a hurdle I need to overcome. Lots of little bits and pieces that I need to fix and perfect, and could use help from other people, obviously. So, I mean, I'm not some insane genius that can figure everything out by himself. Everything has been passed on to me by many other people. So, but in this particular case, I cleaned out the syringe, and then I noticed that there was carbon on the outside for my first round, which was 10 milligrams of adding this carbon solution. And then I added another round of carbon solution, which was another 10 milligrams. There it is right there. You can see me adding it into the main flask, right? Into the main body. And I added more water too. Like, you can see right here. No, it's about the same level. That's way lower. So I have it in my notes. I'm not quite sure exactly how much distilled water I added back into the system. You can see that I definitely added some back though, because it was getting too low. And there's where I added the carbon, the graphite, and this carbon, right? It's the same thing. Okay, and this is where things start to turn a little radical. So you can see that it starts to boil off very quickly from this point. And it's the theory is primarily because there's a deuterium buildup, and the carbon is mediating like electromagnetic pulse waves in the cavity. It's reflecting more. It's dampening the waves from escaping, so the waves are reflecting back into the focal point of the electromagnetic dissipation, like the not dissipation, but the electromagnetic focal point, right? Where the electromagnetic energy is coming from. So it's dampening it from escaping and reflecting back into using refraction, both through electromagnetic waves in light and also what may be sound. I mean, this is where it becomes very theoretical, but the principle behind it is using cavitation and being able to create a harmonic cavity or resonant cavity that bounces out and brings the energy back in, rather than trying to forcefully use outside means to create fusion. Instead, it's a pulsation where you're bouncing it back into the anode or into where the fusion point is. Whether you do it through excitation in high frequency, or you do it in just a DC, which in my understanding is also a very high frequency. That's my theory or hypothesis, is that DC itself is a very high frequency. We just haven't been able to understand the frequency level of DC. Like you can pulse it. Pulse DC is cycle time and duty cycle, but DC itself is on a chemical level or a subatomic level, very, very high in frequency. We just don't quite understand it, and that's something that Tesla talked about, is that when you would flip a switch on DC, its voltage when you had high voltage, it would jump the line and kill people and do crazy stuff. It would shear off the line and jump around because its speed was far exceeding what the copper cable was able to hold. The copper cable was too resistant for it to be able to travel with DC. That's why DC falls off and is very bad at transporting power, because its frequency level is so high. It's according to the chemical composition or the subatomic composition of the material it's created in, if that makes sense. That's very crazy talk, but anyways, this is where it gets really wild, and I have to shut down the experiment because, as you can see, like it starts to boil very, very rapidly, and the flask itself became buoyant and raised up. But also in my apartment, my wife was just on her computer, and the whole apartment filled with steam and kind of smelled like brimstone, because the carbon and the sulfur would be my guess, but it became very radical, and I had to shut it down because I was worried that it would burn something down, or I would short and then blow a fuse and all that kind of stuff. So this was pretty much my last experiment in this realm of hydrodynamic star in a jar stuff, and you can see some of the crazy like pulsations that are happening there in the nickel. And what I'm doing is I'm cycling on and off the power, because I'm trying to find that medium spot, that tune spot. Now I think this can be done via like a signal feedback circuit, like so, understanding what signal needs to be optimized, and then keep maintaining that signal. And then also you have to keep in mind, I have no recycling of the steam. The steam is just going off into my apartment, so I don't have any way to reclaim that excess steam, which also would be very helpful in the experiment. There's many avenues and there's many aspects of this experiment that can be improved upon, but right around this point it became very volatile when it was starting to get, you can see how quickly the flask's water dissipates, and this is at like I said, like 400 watts maximum, and the water is boiling off extremely fast, and then once it gets a little lower, it becomes very, very it literally goes crazy, and it creates almost like a capillary flow along the electrode. Like, that's the best way to describe it, and it just goes nuts. So I got worried, and fortunately I bumped the camera. I wish I had a second camera that would show the whole room, because then people could really see kind of what went on. Unfortunately, I did not have that. So, and then I tried filling it with distilled water. There's my wife right there. Oh, she was reading at the time. You can see the carbon floating around. So then I was trying to refill it, but it just destroyed the experiment when I refilled it. So I think I could absolutely replicate this experiment. It's just, you know, a matter of time, and seeing if nature says that it's something worthwhile, because, you know, if it's not worthwhile, then what's the point in doing it, right? Like, can test it so far, and if nature's saying, hey, this is not fusion or anything like that, then there's no point in doing it. What the heck is this? No.
YouTube is great for people that are just starting a new business.
It is
or small
great.
business owners
That's
like
true.
yourself.
So anyways, if you guys have followed me this far, my crazy ranting and raving, I appreciate it. I'm gonna do more of these live streams. Hopefully, interact with more people as they come in. Right now, not too many peeps up this late or interacting this early, I guess. But let's see. Conscious engineering. See all the different logins I have. Probably way too many. I want to go into this and see if anyone's talking or viewing. Nope. But it's good to check, right?
Just put everything you need to do here, then put who's in charge of it here, and see where everything stands here. Also, it works on your phone because it's 2019. Quick drag it.
Alright. So let's see, it's 5:13. I got a little bit more time. I have to get some sleep. So we'll go into this. This is Google Scholar. I don't know if any of you guys know about this, but there's actually a whole section of Google which you can look up scholarly articles, something that I have spent quite a lot of time doing. And in these, you can find things like LENR. For example, effects of rice husk surface modification by LENR and mechanical properties of reinforced rice husk composite. So rice husk means that it would be a carbon layer. Okay, so Murin Grenier, maximum of uranium fission of conformation of low energy nuclear reactions, LENR via compound nucleus with double magic numbers. Some of this stuff is very, very off the wall, but this one, copper, nickel, magnesium alloy wires. This is something that's I've experimented with myself, actually. Only I use titanium nickel, which is nitinol, which I think is something that is promising in being able to create a oscillating wave ignition circuit, if that makes sense. Like being able to take a negative cathode, negative anode. I get them confused because once you swap the power in to power out, I always get it confused, you know, as far as electrical chemistry. But hopefully you understand what I'm trying to say, and that is that it creates a phonon vibration. So phonons are the transverse waves in a wire that create heat and create sound and create vibration, right? Phonon, not photon, but phonon vibration. Something that you guys should look up if you don't know what I'm talking about. But in a wave containment and with like a wave guide of quartz, of a quartz material, or even aluminum, any type of crystalline structure can potentially produce something magnificent, is my understanding of things. But whether or not it's true, nature decides. So, but let's look into something else. So let's look into one of my favorite is maybe titanium and non-metallic inclusions, which nucleate ferrite, some RC SAW fusion zones, Navy HEY steel. So a lot of fusion experiments come about when they weld things, when things are welded together, and then they look at it under an EDM and they see things that were not expected, besides like sodium and the simple impurities that usually come about. We're talking about things like lead and gold, silver, obviously, but a lot of things that come about in arc welding, especially underneath the ocean. You know, obviously you expect to see magnesium and sodium and potassium. Those are very abundant in the ocean, but then all of a sudden you see some really strange phenomenons like silicates, which still can be explainable, but then gold, silver, lead, and some other strange phenomenons. I know that a lot of other people who have done sonification experiments through, I'm not going to name names, but who have done sonification experiments using ultrasonics. They have ultrasonic transducers, and they create what essentially is like a fusion through the ultrasonic transducers. They end up getting lead and what is it? Two things that are very hard to say, but are both found in solder. It's very suspect, like that they're in solder. So you have to be very careful in purity tests and making sure that things stay clean. And you know, you have to run a clean room when you do an experiment. Like we're talking about electrochemistry. This is and on a microscopic, on a subatomic scale. So it's, you know, it's challenging work. So computer aided detection for I think one of the better documents is fusion. I'm not sure if that's spelled correctly. This is laser fusion. So that's another approach that a lot of fusion experimenters are using, is that they're using laser to create cavitation. It's still cavitation, which I think is very possible. I think the laser can be very possible, but is it scalable? That's the question. I don't think that laser fusion is scalable, and that's unfortunate, but I think that it is a possible avenue to understand and to find out more about fusion, and that is creating a standing wave in laser, in photons, right? To create a fusion incident or a fusion moment in a certain material. So it's very possible to use lasers as your fusion guided, like as a fusion system. And I think China is developing a laser fusion system that's probably the most comprehensive, as opposed to like the force fusions. I call them force fusions, but like the hot fusion reactors, like tokamak, or there's some other ones that Germany is doing now, which are contorted magnetic fields. They're just very forceful, and I don't think that that's the way to go. I think it needs to be a harmonic response according to nature, like using certain systematic resonances according to what the materials you're using, and using waveguides appropriately. You know, like you can't just force it into a confined space. Like confinement fusion is like, it's not how nature operates. It's not how the stars are created, in my personal opinion. The stars are, you know, electrical filaments throughout the skies. That's how I look at it, if you really want to understand my perspective of it. Whether or not it's true, I don't know. I would love to be proven wrong, but I have, in all my research, I haven't yet to find any type of inclination that I would be incorrect in my understanding of not only how stars operate, but it's just fusion in general, like how new elements are created in stars, and how there's a vast amount of energy that's of more of an electrical nature than we're willing to admit. So I don't see. This is all data fusion. Here we go. SPAWAR. Common processing. So SPAWAR use a lot of palladium, which is very well known for its hydrogen absorbency, metallic hydrogen, creating metallic hydrogen. Nickel is the cheaper version of that, and nickel titanium is a hybridized, cheaper version of that. That's the avenue that I've been trying to take more, because palladium is very expensive and it's not something that most people can do. So if you look at the elements, oh, that's strange that popped up. Okay, let's look at the elements here. So as you can see, we have palladium here and platinum here, right? Gold, silver, right? So nickel is above, right? Now titanium is clear over on this side. Kind of weird. If you look at what's on the hydrogen line, I would call it. We have hydrogen, lithium, sodium, potassium. These are all the what the hell? Not transition metals, but oh my god. Crap. The name escapes me right now. Alkalines. Oh my god, the alkaline metals, right? Potassium, rubidium, all these, cesium, francium. These are all the alkalides in the alkali group, right? And those help harbor the hydrogen because they're all within the hydrogen line, right? That's the idea behind it. So that's why a lot of hot fusion experimentalists use lithium, and you know, that's why all electrolytic cells use sodium and potassium. Myself, I use potassium as my ionic medium in my electrolytic cells. So and I could be incorrect with what I'm saying, and I would feel free to, you know, correct me in my statements. That's I'm not, you know, a genius in every field, because this takes a lot of different fields of understanding to truly understand, right? But as you can see, nickel, palladium, and platinum are not only are this section like the most diverse in being able to resist electrolytic degradation. What is it called? It's called decomposition there's another word for it, but they're able to resist the decomposition of an electrolytic cell and things of that nature. Not so much copper, but this area, right? They also bode, or I mean, pardon me, this area, they also bode very high absorbencies of hydrogen, especially palladium has one of the highest absorbencies of what's called metallic hydrogen, which is basically hydrogen in a metal lattice, from our understanding of the subatomic, atomic and subatomic, which is very challenging. So yeah, I just wanted to go over that real quick. Who knows how that will help anyone out there. I'm yawning. Okay. View of dolphin hydrodynamics and swimming performance. Okay, so spy war, fusion. Go back to this. There's some other ideas and experiments that have been carried out, in particular doping. Like, we can go to that actually. It's even on YouTube. Ruby Carrot has a YouTube thing on that. But spy war, fusion. So this is one of the examples, cold fusion. So they use CR39 to detect the emissions of a fusion reaction. So that would be neutron emissions.
Impact solid-state nuclear track detectors, which are also known as CR39.
Yeah.
They create a conical-shaped crater, also known as a track. Sometimes particles will stop within the CR39 material. Sometimes they'll go clear through. These images represent several of the type of tracks you might see from charged particles. The geometry of these tracks is very specific and can be mathematically calculated and thus correlated to particle type as well as particle energy. This next image is a photograph of two actual particle tracks recorded in a CR39 detector. What you're looking at is the edge of a detector that's been sectioned right through the center line of two multi-micron sized tracks. It probably was not an easy thing to do. You can see, as expected, that the track ends in a small tip, a pinpoint, where the particle lost its momentum and came to a stop. Pamela Mossier-Boss, one of the lead researchers at SpaceWar San Diego, who's been performing low-energy nuclear reaction research, historically known as cold fusion, told me that when she looked at detectors from her experiment and she varied the focus on her microscope to focus either on the top of the CR39 surface or deeper within the track, she could clearly see that the area in focus showed a progressively narrowing depth, terminating in a pinpoint, exactly what you'd expect from a real nuclear particle track. I asked her if she could put a video camera on the microscope, but she didn't have one available. So instead I asked her to take a series of 26 sequential still images, one at each stop on the focus knob, each stop focusing deeper into the track. I then assembled the images into a slideshow that automatically advances to each successive image, and this is what you're looking at. Hopefully it gives you a feel for what it's like to be looking through the microscope yourself.
So basically what was demonstrated is that there's high energy, high electron volt energy that would go through CR10 material, which I believe is some type of silicate substrate. I believe it's silicate, but it is supposed to stop, like most people understand, it's supposed to stop beta particles from going all the way through. Like obviously alpha can be stopped by a piece of paper. Beta particles can go a little deeper. It's supposed to capture beta particle decay or fall off from the inverse square law, the distance it from the emission point. So let's go into some more of this stuff. This is very interesting stuff. That is spelled terribly. This is a whole bunch of crap. There she is again. There's a whole bunch of people who've researched into this.
First of all, I'd like to thank the University of Missouri and
Spa War is naval research that really followed. They're electrochemists. Yeah, this is probably the best one. So they really followed the theories of Pons and Fleischmann, or the experiments of Pons and Fleischmann to a T. And what's funny is that, you know, many other universities dismissed them as being accurate during the Bush administration. But what's very interesting, I find peculiar, is most people who tried to replicate it didn't follow it to a T, and they still ended up with some positive results, and they dismissed them and said that it was a false positive. But it's strange. I'll leave it up to you to decide. Just please, if you're interested in this stuff, do your research and go and look, and you'll find some very enlightening studies on basically what is hydrogen fusion reactions that are not done via hot fusion. They're done what's called cold fusion, but they're done through a liquid dynamic medium. So they're done through more of a condensed matter physics rather than using gaseous matter, which makes more sense to me too. In the universe, like, you're gonna have condensed points of energy. It's all about potential energy and the capacitance it stores according to like a hot spot or cold spot, or however you want to look at it. So yeah, and the potential difference between those spots. So yeah, this is a very interesting video.
Scientific prophecy is not to rely on abstract reason, but to decipher the secret language of nature from nature's documents.
One of my favorite quotes.
This is the guiding thing.
This is how you do science, right? Is you ask nature the questions. You don't make ideas in your head and induce theory, right? Induce experiments, inductive experiments. You want to do deductive experiments. Eliminate all probability.
Were two electrochemists, Stan Spock and Pam Boss, both PhDs, and they were working on high energy density batteries. Well, of course, Stan and Pam were both electrochemists, and also good experimentalists.
Well, we were friends, and we talked at meetings, and we talked about cold fusion, and we weren't able to work together until other people in the Navy, the Office of Naval Research people, realized that we had some promising results.
So being electrochemists, they knew a little bit about chemistry and what reactions might be taking place. And also, they knew Fleischmann in advance, so they had some knowledge of what Fleischmann was doing.
I was listening, and I found that there's complete misunderstanding. There's essentially a chaos in there.
Whereas a lot of people set out at that time to try and replicate what they thought Fleischmann had done. And there's a difference between what they thought and what he actually had done. So a lot of people impatiently started with a bulk palladium rod of some unknown origin and electrolyzed against it. When they didn't see results in a matter of hours or a couple of days, they thought, well, this is wrong. And they assumed Fleischmann had made a mistake rather than that they had made a mistake. Well, fortunately, Stan and Pam, being electrochemists, went about it differently.
You have to define your initial conditions. You have to know what you are dealing with.
And Stan came up with the idea of co-deposition, which actually was a brilliant stroke, because in the process of depositing palladium onto the cathode, he was also evolving the deuterium there and loading it into the palladium lattice as it was building up.
What is so
Breeding.
interesting about
Breeding it, basically.
There was people were saying, okay, here it takes so long, several days or something, to charge. And then it takes weeks before the onset of reaction. What happened in the meantime? I knew that I could I could get the high DPD ratio very fast by simply co-depositing. In other words, by plating out in the presence of evolving things.
You apply a small current in the beginning that is large enough to evolve
Create
deuterium from the
deuterium.
solution at the cathode. At the same time,
Create deposition.
with palladium ions, and palladium ions pick up 2 electrons from the cathode, plate out as palladium metal. So you have 2 processes going on at the same time. That's why it's called and you're depositing deuterium from the solution and palladium also from the solution onto a substrate, usually copper, and you form your own palladium already loaded with deuterium as you plate it out.
This is a very well-known procedure. It's nothing new about it. But what does it do here? It eliminates the question, do we have full charge or do we not, and all that, all sorts of questions answered.
Well, the main feature is that you make your own palladium by plating the palladium from a palladium salt out of solution, so you have a high purity of palladium, for one thing, and you make it yourself. You don't have to buy it, you don't have to depend on the metallurgy of some other company. You just make it right there, and so therefore it has a much better chance of being reproducible, I think. And that was the main attraction. It could be a reproducible experiment.
Several things resulted from that. First of all, reproducibility was very high. Second, you didn't have to wait 2 weeks. In fact, we could see evidence of the cathode heating up within a few minutes, where it would be hotter than the solution.
Next question is, that is easy to do. What is difficult, that most people don't know how to do it, and what they will do, they will have it falling down nice block powder.
A lot of them had problems, though, with getting SSC because, just like I didn't know what the problems were. If their cell was too small, they weren't plating out enough palladium, and if their calorimetry was not accurate enough, they would not see it anyway.
The problem is that you have to start with very small current to deposit at least 2 or 3 monolayers of palladium. You see, in this, if the palladium is so thin, it will not take hydrogen or deuterium. Deuterium does not penetrate. If you have deposited, say, you have gold, and then you deposit a little bit of palladium, the first 3 layers, the hydrogen or deuterium will not absorb. And then that gives you the reason that you can build up and the thing will not be falling off.
Okay, it was frustrating because I didn't understand some things at that time. And one thing, my cell was small. The solution were the same concentration as theirs, but they had a much larger cell. So they were plating a lot more palladium than I was. And I later figured out I was only plating 0.01 cubic centimeters of palladium. And typically in my experiments I'd get about 1 watt per cubic centimeter. And such a small amount of palladium was being plated, the most I would likely see would be 10 milliwatts. And my calorimetry could only measure when it was about 20 milliwatts. So therefore I didn't see it, but I didn't understand that at the time. It was only when I got exceptionally high power density would I see an effect. I saw, I think 2 out of 34 experiments gave XSC. When I calculated the power density, because a small amount of palladium deposited, the power density was, I forget exactly, it was something like 60 watts per cubic centimeter, much higher than any normal experiment would have given, but it was enough that I could measure it on my calorimetry. But after the program closed down, I got a chance to go to Japan, work at the New Hydrogen Energy Laboratory. I took some new ideas about co-deposition with me, and also I had a Fleischmann Pons Duracell, which is about this big, and you fit in my little tiny test tube. So instead of 18 milliliters, I had 90 milliliters of solution. But when I played it out, I had 5 times as much palladium on the surface, and that made a big difference. And I also had a much more sensitive calorimetry of the Fleischmann Pons Duracalorimetry. It could measure within 1 milliwatt. And so when I got in Japan, I had a much more accurate calorimetry. I had a much larger amount of palladium that was plated. And I only had time, because I only had 6 months. At the very end, I ran 3 experiments on co-deposition, and all 3 gave excess power, excess heat. 3 out of 3 in Japan, using my new solution and better calorimetry and a much bigger cell, plating out much more palladium on the surface. So I think it is reproducible, but you have to get enough palladium that you get enough heat that you can measure.
A lot of other people had problems in their experiments and getting the reactions they thought they should get.
So the streaming
said, well, it doesn't work. And Stan and Pam were having success.
If you use it correctly, you will have 100% reproducibility. My position or my approach is use everything as simple as you can. Don't complicate things. So now the problem was, okay, we need to find out, is it really producing heat? Well, you can start with calorimetry and do this thing, or you can take a very simple thing. You can take a glass tube, bend it, take a little piece of copper, attach a thermocouple to it, and paste it on, so fasten it to the glass tubing, and plating on one side, and measure the temperature on the back side, so you will know what is the temperature on the thing, and measure the temperature in solution, and you will see. And sure enough, we see immediately excess heat production.
Look at the amount of excess heat produced, and I've heard Martin say this, if you converted every atom in the cell to energy at 3 or 5 electron volts per atom, there aren't enough atoms there to account for the amount of heat that's been produced. So that's how they arrive at the conclusion that it must be a nuclear event.
They measured the temperature on the backside of the cathode where the palladium was too positive, and it was hotter than the solution, which is unusual and shows there's some heat production going on at the cathode.
And that was counterintuitive, because there's more resistance in the solution than there is in the copper cathode. So the solution should be heating up faster than the cathode, and that wasn't the case. So that clearly indicated to us that the source of the heat was in the cathode.
So he didn't tell you how much exactly, but I was developing accurate calorimetry that could measure the excess heat, also, well, mainly the excess power, but power times times is energy. And so we measured the excess power by the calorimetry.
The question was, well, what would we do if we put that light water, normal light water, and prepare the co-deposition light water, and put them in the magnetic field?
There's regular distilled water or DI water.
Well, we did it first day, nothing happened.
You have to breed it.
Second day, nothing happened.
Right.
The third day, we see rising the temperature of the solution. We have a thermocouple in the solution underneath of this one. And then within a minute, boils up, explodes.
Runaways, anyone who's worked in this field for any length of time has probably had a couple thermal runaways, and they've probably spent months trying to reproduce it and can't.
Unable to.
If you calculate, you have to conclude that's a tremendous amount of extra heat.
When we first started this in '89, we had some experiments. One experiment we were doing where I think we were sampling it once every 30 seconds or once every minute. And we came in one morning and the cell was dry, and something had happened. The electrode had disappeared. When we looked at the data, everything was fine. In the last 30 seconds, we didn't see any huge rise or anything. And then the next seconds it was gone. So we missed what happened. Probably the
30-second
best,
intervals.
Reproduction of that I'm aware of is some work that Stan did with Jack D, who's another scientist at the lab who was working this area. And this was the light water in palladium, and in 3 out of the 10 cases, they had a thermal runaway where the
So
cathode
3 out of 10.
was a palladium wire, or platinum wire.
And they have magnetic field
And 2
put in
fell down
place.
into the bottom of the acrylic cell and was hot enough that it melted through and melted the
Yeah,
hole.
acrylic's a bad
So
choice.
the solution through a combination of leaking out the hole and heat, vaporization, disappeared. And he had in 3 out of 10 cases. So that's a pretty significant result. It's hard to identify exactly what triggers it. In all of the cases, it happened after about 3 or 4 days.
Breeding.
And they were doing cycles, maybe 300 milliamps per square centimeter for 90 seconds, and then complete reversal down to 5 milliamps per square centimeter for 5 seconds, and then back up. And they were doing that cycling when it happened.
Well, there was a professor in the seminar at the University of here, UCSD, and there was another fellow, Evans, working for Atomic International. They were using an infrared camera to photograph the surface to look for the heat. They saw rather unusual heat pattern. So when I saw this pattern, I said, why don't we try to do that on co-deposited thing?
Again, that's something that co-deposition allowed us to do that other protocols would not have allowed. In that case, we had a nickel mesh, and I believe it was a nickel mesh, a mylar window, a thin mylar window, and we co-deposited palladium onto the nickel mesh, and we had the IR camera looking at the back side of it.
How do we see spots? Hot spots.
Hot
when you look at
spots.
this. Now, what does it mean? It tells you that the heat is not produced uniformly over the whole volume, but in certain spots. And this spot
Kind of like my balding pattern.
They went on to do many different things in co-deposition, not with X-rays, radiation, tritium, acoustic studies, where they played it onto a microphone,
Yeah.
and they could hear the sounds made by the fusion burst. They tested what magnetic fields do, what electric fields do, how that changes things. We did a lot of studies in that area, and they probably published more refereed publications than maybe any other group that I know of.
I could not really judge the quality of their work, but I knew the quality of their character and their expertise. And so when they were producing these results, and then they published them, they wrote them up in papers, submitted them for peer review, and they were getting published, that provided the shield that I needed to keep them, to try and keep them fun, keep them going. You could say, boy, that was a stroke of genius, and it because it allowed you to do the experiment quickly. There was a huge, significant flexibility. We could co-deposit onto a cathode of about any shape. We could glue a thermocouple right to the back of it, so we, in intimate contact, so we could see
Measure
exactly what we were seeing.
Thermal
new method of doing
energy.
the study without depending on palladium from some method of manufacture, which
Yeah.
would vary. One
You just make your own palladium structures
they came up with their
and
own
substrate.
method of making it right in solution by plating, which gives you pretty much the same quality of plating in every experiment. I think that was a genius stroke coming up with that co-deposition idea.
Co-deposition became the lab rat, because it was so flexible and reliable. They say, is it better to be lucky or good? And I think in the case of Pam and Stan, they were both. those were the two people. Without Stan and Pam, we would not have been involved in it. It would have died. There would have been, you know, some of the other groups, people that tried it and failed, and it would have evaporated into the woodwork, and it would have carried on.
I went to the University of Pennsylvania, and I talked to one professor there, and my question was this: am I capable of doing any research? After all, I'm 10 years out of this thing. Well, it turned out that yes, I was capable. And after 2 years, I got my PhD there, and the end of the story. And then I started working and making trouble for people.
So cold fusion obviously is a very touchy subject, but there is extraordinary amount of evidence that suggests that there's other happenings in nature which we don't really take a good look at, and that's unfortunate. Like, you can look at right here, because I have all this because I'm a digital marketer type of person. You know, the vid IQ score and the SEO is very low. If we were to put in fusion, for example, this would not even make it on anywhere on the top page, right? We have a jazz fusion, you know, fusion energy, right? And this is force fusion. This is hot fusion.
The fundamental currency of our universe is energy. It lights our homes, grows our
Very
food,
simple.
powers our computers. We can get it lots of ways.
It's a great
burning
infographic,
fossil
though.
fuels, splitting atoms, or sunlight striking photovoltaics. But there's a downside to everything. Fossil fuels are extremely toxic, nuclear waste is, well, nuclear waste, and there are not enough batteries to store sunlight for cloudy days yet. And yet,
You can
the
use wind
sun seems to have
and
virtually limitless free energy.
biogas,
Is
yada,
there a
yada,
way we
yada.
could build a sun on Earth? Can we bottle a star? The sun shines because of nuclear fusion. In a nutshell, fusion is a thermonuclear process, meaning that the ingredients have to be incredibly hot, so hot that the atoms are stripped of their electrons, making a plasma where nuclei and electrons bounce around freely. Since nuclei are all positively charged, they repel each other. In order to overcome this repulsion, the particles have to be going very, very fast. In this context, very fast means very hot. Millions of degrees. Stars cheat to reach these temperatures.
Okay, so what is the hottest thing that we're able to create on this planet? As far as my research and my understanding, it would be an electric arc is the hottest thing. Like a lightning bolt, for example, has, you know, hundreds of times more heat than the surface of the sun, according to our measurements. So, you know, it's something to consider.
They are so massive that the pressure in their cores generates the heat to squeeze the nuclei together until they merge and fuse, creating heavier nuclei and releasing energy in the process.
So this is where I disagree with a lot of the standard model, is that there's not a squeeze happening, it's more of an oscillation according to semantics. So there's like a in the universe there's positive and negative nodal points in three-dimensional planes, and it's, you know, something that's very hard for us to comprehend. I feel I can be completely wrong about this, but these nodal points create standing wave vibrations, which, you know, in some areas you have a condensed amount of hydrogen that is cold at its core, and that sounds completely ludicrous that a star would be cold at its core to create such extreme heat, but the focal point of a star itself would be extremely hot. But if you look at it in electrical physics, you know, electrical engineering principles, the cathode, the negative side, can possibly have a cold point. Like it could be cold compared to the other side. Like, it's a potential difference between the two. And if you look at like thermodynamics, and especially in the Seebeck array, which I think earlier I said was the Seeman array. That's so wrong, but Seebeck, and any type of potential difference, that's how you create voltage, right? Is any type of potential difference. It can be thermal, it can be kinetic, it can be, any type of vibrational differential can create energy, because it's, you're creating a void where nature wants to balance it out. You've created a high and a low spot, and nature always wants to equalize into a ground state. So, that being said, something like a star, I don't think, my personal opinion, is like built upon gravity squeezing it so much as it is built upon it's oscillating according to another local body that also has a tremendous amount of energy, and they're feeding each other through basically lines of energy, plasma sheaths, plasma lines, and we aren't able to really see it because it's not in. It's like a DC. It's in frequencies that are far beyond our understanding, because we look at things very much based upon light and the electromagnetic spectrum of light, which is very limited. But there's far greater frequency ranges that we are just unable to visualize or unable to see as far as sensors, and we do delve into those realms when it comes into gamma and X-ray, and going into the higher realms, and then also infrared, and going to the lower realms. But it's very difficult for us to fully conceptualize. That's my take on it, and I could be completely wrong. I'm fine with that.
It is this energy release that scientists hope to harness in a new generation of power plant.
This is what I'm saying is
reactor.
Forcefully.
On Earth, it's not feasible to use this brute force method to create fusion.
Brute force.
So
and they
if we
admit
want
it too.
to build a reactor that generates energy from fusion, we have to get clever. To date, scientists have invented two ways of making plasmas hot enough to fuse. The first type of reactor uses a magnetic field to squeeze a plasma in a donut-shaped chamber where the reactions take place. These magnetic confinement reactors, such as the ITER reactor in France, use superconducting electromagnets cooled with liquid helium to within a few degrees of absolute zero, meaning they host some of the biggest
amounts of potential
gradients in the known
Exactly.
universe.
Huge amounts of potential gradient.
The second type, called inertial confinement, uses pulses from superpowered lasers to heat the surface of a powder
That's the laser pulsation that I was talking about.
briefly making the fuel hot and dense enough to
creating
fuse.
standing waves as well.
In fact,
Cavitation.
One of the most
That's what makes it so
lasers
hot.
in the world is used for fusion experiments at the National Ignition Facility in the US.
Yes.
These experiments and others like them around the world are today just experiments.
It's a Z machine. That was the
Scientists are
Chinese
still
version I was talking
developing technology. And although they can achieve fusion, right now it costs more energy to do the experiment than they produce in fusion.
That's correct.
The technology has a long way to go before it's commercially viable.
It's always 20 years away.
And maybe it never will be. It might just be impossible to make a viable fusion reactor on Earth.
I don't think it is impossible.
But if it gets
Nothing's
there,
impossible.
it will be so efficient that a single glass of seawater could be used to produce as much energy as burning a barrel of oil with no waste to speak of.
That's the real challenge.
This is because fusion reactors would use hydrogen or...
Who's going to make money off of being able to take some ocean water and turning it into as much as a gallon of fossil fuel? Nobody's going to make any money off that. There's no investor that wants to put money into it, so it needs to be governmentally subsidized, or it needs to be into the public sector where we can do it ourselves through open source hardware.
Or helium as fuel, and seawater is loaded with hydrogen. But not just any hydrogen will do. Specific isotopes with extra neutrons, called deuterium and tritium, are needed to make the right reactions. Deuterium is stable and can be found in abundance in seawater, though tritium is a bit trickier. It's radioactive, and there may only be 20 kilograms of it in the world, mostly in nuclear warheads.
Once it's created, it's
incredibly expensive.
decay
So
time is
another fusion buddy for deuterium
very quickly.
instead of tritium.
Very quick.
Helium-3, an isotope of helium, might be a great substitute.
Also very fast, though.
Unfortunately, it's also incredibly rare on
Yeah.
Earth. But here,
And decays
the
very
moon
quickly.
might have the answer. Over billions of years, the solar wind may have built up huge deposits of helium-3 on the moon.
So let's mine
Instead
it,
of making
right?
helium-3, we can mine it.
Right.
If
Let's
we
mine
could sift
something
the lunar
else.
dust for helium, we'd have enough fuel to power the entire world for thousands of years.
Why don't we just breed our own
One
helium?
more argument for establishing a moon base, if you weren't convinced already. Okay, maybe you think building a mini sun still sounds kind of dangerous. But they'd actually be much safer than most other types of power plant. A fusion reactor is not like a nuclear plant, which can melt down catastrophically.
Not at all.
If the confinement failed, then the plasma would expand and cool, and the reaction would stop.
And be done.
Put simply, it's not a bomb. The release of radioactive fuel like
It's
tritium
fusion.
could
It's
pose a threat to the
inward, not
environment.
outward.
Tritium could bond with oxygen, making radioactive water, which could be dangerous as it seeps into the environment. Fortunately, there's no more than a few grams of tritium in use at a given time, so a leak would be quickly diluted. So we've just told you that there's nearly unlimited energy to be had at no expense to the environment in something as simple as water. So, what's the catch? Cost. We simply don't know if fusion power will ever be commercially viable. Even
won't.
if they work, they might be too
Nope.
expensive to ever build.
Too expensive in what way? So we build something that actually works and creates an abundant amount of energy, but the person who puts the money in to build it, what do they get in return? That's how our social dynamic, our social engineering is designed. They get nothing in return. So that in and of itself is creating the paradigm that is stopping us from creating a lot of abundant engineering and a lot of abundant technologies, unfortunately. Because if you look at engineering in general, especially in an energy sense, is human energy and engineering, social engineering, is the precursor to all other engineering aspects, to all other, social, all other designs, like whether they be social or civil or electrical, mechanical. It doesn't matter what type of engineering. The precursor is always social. How we have designed our social, socio-economic structure. That always comes first. Always.
The main drawback is that it's unproven technology. It's a $10 billion gamble, and that money might be better spent on other clean energy that's already proven itself. Maybe we should cut our losses. Or maybe, when the payoff is unlimited clean energy for everyone, it might be worth the risk. Videos like this one powers our computer.
So unicorns are mythical, okay? A rainbow is something that you chase but never can reach. The very concept of free energy and something that's abundant for everyone to use is unfortunately mired in our social dynamic and how we feel, how we think and feel as a species. And what I mean by this is that you can't find a unicorn, right, if you're not willing to look through the forest, like, and believe that there's a possibility of it, right? So and oftentimes you have to step outside of the box, like you have to step outside of the forest. I don't know, it's hard to describe. It's more of a spiritual quest than it is a physical one, and that's what makes it so difficult. Is free energy doesn't exist because we have a monetary structure. Like, there's no way that we can ever free energy if our very root of who we are as a human species, like as a species, is based upon energy being commoditized. Like, commoditized, I don't know if that's a word, but being able to, every person has a certain set value according to how much work they do. I mean, that it makes sense. It's understandable that that's where we're at, but there's so much more potential that can be unlocked by the human species. And many people, if instead of focusing on a set structure, we focus on like how much potential someone has, and understanding and unlocking their potential, like, and asking the biggest questions, which are, who am I, why am I here, you know, what am I, you know, the who, what, and why, the biggest spiritual questions that everyone can ask. And this is kind of where, you know, it's a little bit wild, but spirituality and science meld, they merge and become something that's very powerful and can bring us into a new age, in my personal opinion. But, you know, thinking that things are locked into a preordained or a preconceived systematic structure where there's no way that we can, you know, have abundant energy, you know, just by thinking that there is no way we can have abundant energy, if that makes sense. Like, unless we decide that we want energy to be free and we want energy to be abundant, because nature already has it free. Like, the sun gives us energy and asks for nothing in return. There's energy all around us, swells of energy. There's more energy in a cup of ocean water than there is in a barrel of oil. I mean, because it's a far more condensed version of energy. So, you know, it just depends on how you look at it. So that's my rant for the night. I should probably call it a night too, or a morning. It's like 6 in the morning, and this was just some tests I'm doing. I think I have a cut from the missus. She scratched my head yesterday. I won't tell you how and why. She was defending herself. Anyways, I hope you guys enjoyed some of this knowledge and information, and some things that I researched many years back that I'm just kind of re-researching and re-going over. Obviously, you can see that this SEO, you know, these people are on top because they have a very fluffy video that everyone can consume and is very malleable. Whereas the spa war stuff is a lot more intellectually intensive. Like, you have to really look at it and do your research, maybe watch it a couple of times to really understand it. This is easy and fluffy and easy to remember. It has infographics with cartoons, you know what I mean? So, you know, if you're really interested in this stuff, then hit me up anytime. Please subscribe. Let me know what you think about these live streams. And yeah, follow me. And I'm basically, I want to build a community of like-minded people. So if you're interested in this stuff and you're really passionate about creating clean energy systems, then you know, SciTech Syndicate is your place, and helping the cause is what I'm all about. So much love to you all, and until next time, peace.